And we're back. And we want to we're going to get started on the get started on what are we getting started on? I'm losing my train of thought. He didn't change his state. And so I want you to answer these two questions over here on the side. How does the quantity of heat absorbed by a melting solid compare with the quantity of heat released when the liquid solidifies? And how does the quantity of heat absorbed by a vaporizing liquid compare to the quantity of heat released when the vapor condenses? Okay, so compare those two things after we finish our lecture here. So, heats and changes in state. We're going to start with the heats of fusion and solidification. So what happens when you make ice water? Well, we know from earlier that the heat from the higher temperature liquid water will flow into the lower temperature ice cubes. Now, part of this effect is bringing the ice cubes up to the melting temperature of 0 degrees Celsius, because they're usually colder than freezing. That's how they stay solid. And so they're not just constantly on the border of liquid or solid. So they're usually colder than freezing. And this process stops when the water reaches the same temperature as the ice. Okay, remember this is called thermal equilibrium. What temperature do you think that would be? Well, when the water reaches the same temperature as the ice, that means they're both at the same temperature, and you actually have some of the water turning into ice and some of the ice turning into water. And so this is going to be at 0 degrees Celsius, which is both freezing and the melting point of water. It's for both of them, and because you can go in both directions. So, what if the ice was on the kitchen counter? Well, the ice would still try to reach thermal equilibrium with the counter, but the counter has a significant amount of heat capacity. And so the ice temperature would continue to increase to its melting point. But again, what temperature is the melting point? It is at 0 degrees Celsius. And it would remain there as the heat flows from the kitchen counter into the ice cube, melting the ice. The kitchen counter certainly isn't going to melt. And it's certainly not going to freeze because it's already a solid, but it has significantly more heat capacity than the ice. And heat will continue to flow, and here's the kicker, flow into the ice until all the ice melts. Only after that time, then, the temperature can start rising for the water. Only after the solid has turned completely into liquid. This effect, okay, is a situation where there is no change in temperature. So if there's no change in temperature, how do we account for the heat flow into the solid ice while the temperature stays constant? Okay, this is a problem for us because Q equals MC delta T fails. We don't have a delta T. There's no change in the temperature. So we need a new situation, and what we get is the latent heat of fusion, or just called the heat of fusion. The L stands for latent. It is the heat of fusion. Let's place this fusion in the right spot here. Okay, it is the heat of fusion. The heat of fusion is the amount of heat needed to change 1 gram of solid into 1 gram of its liquid. And for water, that amount is 334 joules for every gram of ice. Why is it not joules per gram degree Celsius? Gram degree Celsius? Because there's no delta T. It's only mass times the heat of fusion. So for every gram, you need 334 joules to convert it into water. The temperature is irrelevant. It is the amount of heat. This is just the amount of heat that flows in during the endothermic process. Okay. The quantity of heat absorbed by a melting solid is exactly the same as the quantity of heat released when the liquid solidifies, so that if we were to freeze it again, that the delta heat of fusion, that the change in the heat for fusing the ice, for making ice, equals negative melting ice. Making ice and melting ice. Okay, so for it, the two of them will be exactly the same direction. Okay. Now, a very similar process happens at the other end at the next phase change up, in the next proper phase change. Okay, it happens when changing from a liquid to a vapor. Okay, so liquids will absorb heat at the same temperature. Okay, in other words, it will boil until all of the liquid has turned into vapor. How many of you have made the mistake of when you are trying to boil water for pasta or something, and you're just trying to boil a little bit of water in your pan, just trying to heat it up, and the water boils away? I've done this, and I've turned my pan. I've almost started a fire in my apartment when I was back in college, trying to cook something, because the same sort of thing happened. But we have the same kind of process, that the heat that is going into our evaporating the liquid is this LV, this latent heat of vaporization. The amount of heat needed to change 1 gram of liquid into 1 gram of vapor. It's the same thing. Okay? And the latent heat for the vapor, for the water, is going to be 2,260 joules per gram. It's actually significantly higher than that of ice, than melting ice. That quantity of heat absorbed by a vaporizing liquid is exactly the same quantity as the quantity of heat released when the vapor condenses. So that the heat of vaporization, the change in heat in vaporizing, equals negative the heat in condensing. So let's do a practice here. How much heat is absorbed in a 10-gram sample of water at 100 degrees Celsius when it turns to vapor at 100 degrees Celsius? Well, our heat equals our mass times our latent heat of vaporization. So our mass is 10 grams, and our heat of vaporization is 2,260 joules per gram. So we just multiply them, and we get 10 grams times 2260 gives us 22,600 joules just to evaporate the water. That's 17.3. Pretty quick. We'll sign out here, and we'll see you guys next time.